Hello everyone, welcome again. Chapter 3, Derivatives. We move to the next part of the series, which is about derivative as a function. To give you a gist of this, we're saying that we saw previously that f prime of x naught, which is derivative of the function at a point, exists if you were able to find the limit of the difference quotient. Now, here we say it's derivative as a function, no longer at a point. So what this means is that if we can find derivative at every point on a given function, then the entire function has a derivative. And so that is the point we're trying to make so that we can understand this process of finding the derivative of a function, and we call that process as differentiation. And then we say the function is differentiable. Okay, I'm going to write this definition here. So here we go. If f prime exists at a particular x, then we say f is differentiable at x. This implies that f has a derivative at x. And so you can notice here that the definition no longer has f prime of x naught, but it has f prime of x. So x would be every point. It means the entire function. So we're talking about every point in the function. Okay. So f prime of x equals limit h approaches 0, f of x plus h minus f of x all over h. And so we say if f prime exists at every point on the function, of course on its domain, then we call f differentiable. Okay. So if they say suppose that f is differentiable, and the theorem goes on like that, that in the background means that f prime of x exists. Okay? And the process of calculating a derivative is called differentiation. Okay? Now we have an alternative formula for the derivative, and I'm going to put that up here, and then we'll look at some problems. So here we have f prime of x to be limit z approaches x, f of z minus f of x over z minus x. Now this formula is an alternative, but the advantage of this formula is that you can see it more visibly as y2 minus y1 over x2 minus x1, where x2 is kind of approaching x1. Okay, instead of x2 and x1, we have z and x. So that's the only change here. Whereas here, the traditional formula involving the h, that is helpful, especially when we see that only one point is given and you can generate the other point with a plus h. So both formulas have their advantages, and you just want to use the one that is useful or meaningful to your given problem. So let's start with the first one. It says differentiate. Notice the language. They could say differentiate or find the derivative. X over x minus 1. So if they simply say differentiate, then you know that because of the process of calculating the derivative is known as differentiation. You know they are not talking about the tangent line, although slope of the tangent line is the derivative. You know that that's not the interpretation they want from this particular problem. They want us to provide it in the calculus form, which is the derivative. Okay, so we are asked to find f prime of x is to be found or calculated. Okay, so then we have two options. We have two formulas, right? We'll use the one that we generally use. So using definition, I'll say f prime of x, not x naught, because they didn't give us a particular point. They just said differentiate the function. And because of the definition that allows us to differentiate the function in its domain, we have this traditional definition. All right, so just to move into the calculations more easily, I would like to insert f of x plus h right away. So your function is f of x. So in the place of x, you now have x plus h. So please watch what I'm doing. I am inserting parentheses for wherever I intend to substitute the x plus h. Okay, So that is for the first part. Minus f of x is x over x minus 1. I'll put that also in parentheses so that we can handle them individually. Again, this leads to a complex fraction situation, so we're going to focus on the numerator. I just want you to watch what I'm doing, so or you could pause and do it on your own, come back, fast forward it to check the answer. Taking the LCD. So basically I'm cross multiplying, and then I'm going to FOIL now and simplify them. I do not want to FOIL the denominator because by now we've seen the pattern that the numerator will have an h pulled out and that h will cancel with this bottom h. So there is no h to eliminate here, so I don't want to distribute the denominator unnecessarily. Well. No. And now we can substitute 0 for h. Which comes out to be negative 1 over x minus 1 times x minus 1, which is the same as negative 1 over x minus 1, the whole squared. So to kind of put them all together, f prime of x is negative 1 over x minus 1, the whole squared. In this section, we've made a powerful move from finding the derivative at a point to finding the derivative of the entire function. And what's really spectacular is we can use this to actually find the function, the derivative at a point. So if my x value is, say, 5, then I can find the derivative at 5. If my x value is 7, I can find the derivative at 7. If x is negative 3, I can find the derivative at negative 3. So this gives me the flexibility because it's like a template for the entire function, and I can evaluate at any point to find the slope of the tangent line, or the derivative in this case. Here is the next problem. We have two parts here. A says to find the derivative of f of x, which is equal to square root of x, for x greater than or equal to 0. And part B says find the tangent line to the curve y equals square root of x at x equals 4. Let's focus on part A. Part A wants us to find the derivative. So from the language, it becomes clear that I need to find f prime of x. To find f prime of x, we use the definition. So f prime of x, limit h approaches 0, all over h. So f of x plus h, right? Now we have f of x given to be square root of x. So in the place of x, I plug in x plus h. So wherever x occurs, I'll have x plus h. So I'm going to put parentheses under the radical. And I insert x plus h for the entire radical. Please do not put it at the end of the radical outside it. It has to stay inside the radical. All right. Now, if I plug in 0, we're going to have 0 in the denominator. There's no way to factor out the h. So what is the algebraic move to handle radicals stuck like this? We've seen this before. In fact, we use the conjugate technique to handle these kind of radical situations. So then we will multiply up and down by the conjugate of the numerator. The conjugate of the numerator is square root of x plus h plus square root of x, equal and opposite, and match the same thing down here to preserve the value of the expression. And now we are ready to multiply across. You can FOIL it, but remember again in the conjugate method with radicals, it's always, the conjugate method is always the difference of squares. And we know that that's a plus b times a minus b is a squared minus b squared. So it's this idea in conjugate. So we're going to use that idea and simply take the square of each term. Well, the denominator is going to look a little complex, but we know it's all going to go away once the h cancels off and we apply h or substitute for h as 0. So bear with that large expression until you're ready to simplify it. The square root and the square will undo each other, and so we have this. In fact, you could have cancelled it in the same step, understanding that you're doing 2 steps in one. All right, they're close. Plug in h as 0. So we get square root of x plus 0 minus square root of x. I apologize, I've been having that minus throughout. You see the plus there? I don't know how I missed the plus. Okay. And then we have 1 over 2 square root of x. So let me come over here. This was f prime of x. F prime of x gives us 1 over 2 square root of x. So this was part A. This is the derivative of f of x, which was square root of x. Then we go to part B. Let's go back and see what part B said. Find the tangent line to the curve y equals square root of x at x equals 4. Well, it's the same function, so the derivative would be the slope of the tangent line. So we'll write that little note here. Okay. Since the derivative from part A is the same as the slope of the tangent line. We need to evaluate f prime of 4. Because remember, slope of the tangent line is at a point. And so this was for the entire function. So at a point was given to us in part B. And part B said at x equals 4. So that is our, that's a point at through which the tangent line passes. And so we're supposed to find f prime of 4. And let's do that. So f prime of 4 will be 1 over 2 square root of 4, which is 1 over 2 times 2, which is 1 over 4. So the slope of the tangent line at x equals 4 is 1 over 4. Now that we have the slope, we need to find the equation, because that's what they mean by find the tangent line. The equation of the tangent line is, it's y minus y1 times equals m times x minus x1. In order to help us answer that, we were given just the x coordinate of it, right? So this implies your f of 4, which is your y coordinate, is square root of 4, which comes out as 2. So the coordinate is x, which is 4, comma y, which is 2. We need this. We need the slope and the point. So we've got the slope to be 1 over 4, and we got the point to be 4, comma 2. We're going to use that to plug in here. Y minus 2 equals m times x minus x1, which is 4. That's y minus 2 equals x over 4 minus 1. Add 2 on both sides, we get x over 4 plus 1. You can put it as x over 4, or you can separate them out and say 1 over 4 times x plus 1 if you want to see the the slope, explicitly. So you'll understand that in Math 4A, we have various ways of expressing the answer, and they're all equivalent answers. And it just depends on how much you would reduce and how you would even present it. So in this case, we're presenting it in two ways. One is a regular expression. The other one is intentionally separating the coefficient of x so that we have the slope visible to us. Here are some notations for derivatives. Now, the derivative concept was discovered both by Isaac Newton and by Leibniz. So they both kind of discovered at about the same time through their own approaches. But therefore, they used certain notations that were different from each other, quite obviously. And when it came to light that they both were working on it, and at those times it took long for it to for their discoveries to come to the general consensus. It was kind of challenging for people to say, okay, I'll choose this notation over the other notation, and that could have upset the two mathematicians. So then, depending on what approach they used, they used these notations interchangeably. And this is what we get from all those in different types of notations. So we have f prime of x. We've seen that. If you don't write it as a function notation, you can simply say y prime. Then we have dy over dx. This is the same as change in y over change in x. So this is convenient in physical sciences, because there you want to see the change of reaction of something over time. We want to see the change in the position of an object over time. So for all those purposes, this notation comes in handy. df over dx. There's a huge application in economics that comes from calculus. So you can see that they use this kind of notation. Sometimes, advanced studies, they use all these kinds of notations. Honestly, I personally haven't used much of these, but I've seen these in use in some textbooks. So we have all these notations. Now, just for the sake of this course and for the lesson here, I will be using interchangeably one of these three notations, right? Now, under limits, we have seen that the left-hand limit must be equal to the right-hand limit for limit to exist. And if it doesn't exist, meaning if the left hand and the right hand are not pointing to the same values, we would just say one-sided limit exists, isn't it? Same idea here for derivatives too, because derivatives, as you can see, the definition of the derivative is itself a limit as h approaches 0. So if it exists, good for us. If it doesn't, we can see that there are possibilities for one-sided limits to exist. Therefore, we call it one-sided derivatives. Okay. So if you have an interval, so let me say here, differentiable on an interval one-sided derivatives. For one-sided derivatives, as you can see here in this graph, if we approach, so say this is the function that runs from a to b, and if we call this y equals f of x, if you approach the point A from the right, okay, so to the right of A, that's this, right? So you approach A from the right of A. But if you approach A from the left of A, there is no function to the left of A. So in this case, we can clearly see that only a right-handed limit would exist, therefore a right-handed derivative. Likewise, if you approach the point B from the left, then we have a left-handed derivative that exists, but we don't have a right-handed derivative here, meaning we don't have a limit that exists from both sides. So in terms of derivative, which is seen also as the tangent line, you can see that at this point, if you keep approaching this, with a line, with the tangent line, you see that this becomes the tangent line, and so we have the right-hand derivative. And on this side, if we were to keep drawing these tangent lines at every point and come to this point, you see that that's where you have the left-hand derivative. So we're trying to explain in this area that we can have one-sided derivatives also. And that is true in functions that do not go endlessly but have a start and end point, or one of them. One end starts at a point but goes indefinitely in the other end, and vice versa. Let's take a look at this problem. Using the definition, calculate the derivatives of the function g of t equals 1 over t squared, and we need to find the derivatives at these three specific points. Okay. Now, if we were trying to find the derivative of a function at a point, then we would individually do them for each point. But now that we know that we can find the derivative of a function, the entire function, we can first do that so that you get a generalized template for that derivative. And then for each specific point, we can then plug in those points in the place of t and evaluate it. And that's going to be our approach here. We will first find g prime of t. For a quick recall, we know that our definition is f prime of x is limit h approaches 0, f of x plus h minus f of x all over h. Let's remember to translate this for our g function with the variable t. So g prime of t is limit h approaches 0, g of t plus h, right, minus g of t all over h. So g of t plus h, so that's 1 over t squared, and therefore it's going to be 1 over t plus h, the whole squared, minus 1 over t squared. That's all in the numerator, divided by h. Again, when we reach this point in the problems, the upcoming problems, those are good places for you to try this problem on your own by pausing the video, especially when you're trying out the LCD and so on. It's really helpful. Okay. Now, in this problem, I'm going to do the flipping of the h right in this step. Okay. So I'm going to take the LCD and then cross multiply. Apologize. T squared minus okay, that's the numerator times the flip of the denominator. Okay, so we got that. So I've taken care of it right here. I do not wish to expand the denominator again, because remember this h that I'm just writing now, that is the one that's expected to cancel off with an h on the top there. So this h is going to we're going to plug in 0 for this h. So leave that h in the square form itself. And remember to distribute the minus. Notice how we pulled out the negative h, and so what's in the parentheses will be positive. You can keep it in the negative form too, that's not a problem, because usually it's only the h we're interested in, not the negative sign. So it's very likely that we're going to have the negative sign. Anyway, going back in. So now it's time to substitute for h as 0. That's negative 2 over t squared times t squared. There is a t on the top, so that will cancel one of the t's. And so we are left with negative 2 over t cubed. So let me write it out together here. G prime of t is negative 2 over t cubed. All right, so this is the derivative. Let me put it in a different color. This is the derivative of the function g of t. Now we're going to use this to evaluate at those individual values. So first let's do g prime of negative 1. That's what we were asked to find. So g prime of negative 1 would be negative 2 over t is negative 1, right? Negative 1. Negative 1 when cubed gives back a negative. So negative 2 over negative 1, which is positive 2. So g prime of negative 1 is positive 2. Let's try the next one, which was g prime of 2. And that will be negative 2 over, in the place of t, you're going to plug in the 2. So I have that there. There was no sign for 2, so the negative 2 will be on the top, over 2 cubed, which is 8. And that reduces to a negative 1 over 4. And then the last one was to find g prime of root 3, which is negative 2 over root 3 the whole cubed. Root 3 the whole cubed would be root 3 times root 3 times root 3. So root 3 times root 3 is a 3. So you'll have a 3 root 3 in the denominator. And that will be your answer for that. All right. So we'll do a similar problem now for the next one. Find the derivatives. Okay. And then they give us the function r of s is square root of 2s plus 1. I'm using a lowercase s, it is or case sensitive here. So watch out for the r and the s. So the variables are r and s. I mean, the function is r and the variable is s. Okay. So let's compare our answers at the end of the problem. R prime of s will be limit h approaches 0, r of s plus h minus r of s all over h. I'm converting this for our problem based on the definition. This is a familiar situation. We've seen the radical, and we know that we have to use the conjugate technique. Now multiply the top using difference of squares. As always, I'm not going to do anything. You cannot really do anything to the denominator. It looks big and scary, no problem. We know that it will be sorted in the end. You remember to distribute this minus. I did two things in one. I got rid of the square root and the square. They undo each other. So I wrote down what was inside, and I made sure to distribute this minus to the second part of the term. Okay. Now, because we have seen this type of problem over and over now, I'm going to do multiple steps in one. So please follow along with me to see that you are tracking with me. Let me quickly check. That was a plus 1 there. Minus. Okay. So the 2s and the minus 2s, they go away. The plus 1 and the minus 1, they go away. Okay. That's the first step. In the second step, we would be left with 2h over h. And so I can cancel off that h and this h. Okay. Bad color choice, I think. Let me try this color. Okay. right? So h and h will go away. You're now in the third step. Now you're left with 2 on the top over this whole thing in the bottom without the h, right? And so we also know that in our fourth step, we will substitute h as 0, okay? So this term will go away, okay, the green term. So pink is the first step, yellow is the second step, and green is the third step where I plug in h as 0. So after you've plugged in, you cannot still have the limit, right? So all you have now left is there's really 2 in the top, everything else is gone, over square root of 2s plus 1 plus square root of 2s plus 1 in the denominator. Can you see that? So this really helps us to eliminate a lot of these steps because these are lengthy expressions by themselves. Now you see that we are not multiplying these two, the square root of 2s plus 1 and the other one, they're not being multiplied, that they're being added because they are like radicals and they have the same radical. They should, if like radicals are radicals that look alike, isn't it? They must have the same root and the same radicand, and that's what we see here. And therefore we have 2 times 2s plus 1. And that also cancels off with the 2 on the top. And so we're left with 1 over square root of 2s plus 1. Bringing all this in perspective, all this started with r prime of s, and that was 1 over square root of 2s plus 1. All right? And this was nothing but our derivative of the function r of s. We usually write f of x, but here it was r and s. All right, now we have the ones to evaluate. So first one was r prime of 0. 2 times 0 plus 1. In the place of s, you plug in 0, and we get 1 over 1 over square root of 1, which is, I'll just put it like that. That gives us 1. Then we have r prime of 1. 1 over square root of 2 times 1 plus 1. That gives us 1 over root 3. Cannot simplify that any further. Then we have r prime of half. 1 over square root of 2 times the half plus 1. And you know that the 2's will cancel off. That will be 1 over square root of 3. And suppose that was good for us. Then we'll do another problem. And I'm going to slowly introduce the other notation that we use. Okay, so here we go. Find dy over dx if y is 2x cubed. Okay, remember, this was one of the notations that indicated the derivative. And this is particularly used when we don't have the equation given in the function notation, like f of x. Instead, if they just say y, we can use dy over dx or sometimes even y prime. Okay, so notation for derivative. You can also use y prime. So they say find y prime. If y equals this, that means finding the derivative. But let's use this notation that they've given us. So dy over dx is the same as f prime of x. Limit. So in these cases, you'll have to kind of reconsider the y as f of x because we've been kind of trained to think of it as f of x plus h minus f of x, right? And so if you have it in the y notation, sometimes it can be not immediately explicit to us. So no problem. So we have 2 times x cubed. So in the place of x, I now have x plus h. So I'll leave a spot to plug in x plus h. And then remember, it's cubed. So the a plus b, the whole cube formula, is basically a cubed plus b cubed plus 3ab times a plus b. Okay. Or if you didn't remember the formula, you're basically multiplying it 3 times over. So you'll have to FOIL these two, and that result will have to be distributed to a plus b. So your call. Coming back to the problem, because I'd like to get them individually, this 3ab times a plus b, I've also kind of distributed it. That's coming from the last term there, all over h. Let's go ahead and cancel off the ones that are alike. Obviously, we're going after the ones that are non-h terms. And so we've got those terms kind of clear right there. And then we have a 2 and an h that can be pulled out, okay? And I know that, for instance, this and this, they are like terms. This and this, these two are like terms. So collect all the like terms, combine them, and so I'm going to do them all in multiple steps. Okay. So this and this, 6x squared h. This and this, 6h squared x. After combining the like terms, this is what we're left with. And so if I pull out an h from the numerator, we will have, I can even pull out a 2, but it's only the h that's going to cancel it off, so it's not going to reduce it otherwise. So I have 6x squared plus 6xh plus 2h squared all over h. Cancel it off. Then I'm going to plug in h as 0. That's going to be 6x squared plus 6x times 0 plus 2 times 0 squared, basically giving us 6x squared. So in other words, dy over dx is 6x squared. And this is the derivative of y. dy over dx is the derivative of y. So you can see that we used f of x concept to get the answer here, but then you always respond to the original question, which was in terms of y, using dy over dx. So we found the derivative of y. Okay, we previously saw that for a limit to exist, we needed the left-hand limit to be equal to the right-hand limit. Similarly, for a derivative to exist at a point, let's say x equals c, then you should be able to find the left-hand derivative and the right-hand derivative at c to be the same number. So your left-hand derivative must be equal to the right-hand derivative. What this implies is if f has a derivative at a point x equals c, that means the left-hand derivative and the right-hand derivative are the same. The only conclusion you can draw is that f is continuous at x equals c, isn't it? Because you found the derivative from both directions, and you know that it implies that f is continuous. Then f is continuous at x equals c. But just because a function is continuous does not mean that it has a derivative at that point, okay? Meaning you can't do the reverse of it. And I'm going to show you instances where that is the case. Okay, so one thing is sure, that differentiability implies continuity. Or in other words, differentiable functions are continuous. You cannot say the same in reverse. So I'll just say, however, continuity does not imply differentiability. Now, therefore, our natural question would be, when does a function not have a derivative at a point, right? So let me write that question here. When does a function not have a derivative at a point? So we can think of, two instances where this will have, a function will not have a derivative. So this is, it implies the derivative dne, you remember that, does not exist. If the limit is not finite, or is a vertical tangent. What's wrong with a vertical tangent? Vertical tangent is basically a vertical line, and the slope is undefined for it. So for these situations, you'll have that problem. Likewise, remember that differentiation is a smoothness condition. When I say smoothness condition, remember that is what it implies when we say derivative approaches the same point from the left and from the right. So that limit would work only if the differentiation is a smoothness condition on f. So if the function, if the graph is not smooth at a point, if it's pointy, those are the places where you will not find a derivative to exist. So here are some examples, okay? So here are some examples where derivative does not exist at that point. So we have a corner. If we have a corner, then the one-sided derivatives will differ, okay? What they're saying is that the left-hand derivative will not be equal to the right-hand derivative. Another familiar instance is, think of the absolute value function. Okay. So at 0, this is a continuous function, by the way. This is a continuous function, but it is not differentiable at 0. Okay, so this is a classic example of how continuity does not imply differentiability. This is a continuous function. Absolute value function is a continuous function, but it is not differentiable at 0. Because if you think of this, if you approach 0 from the left, okay, from the left, so that means your pink piece on the left is actually a negative slope. It's a decreasing line, right? So the slope is negative. So left-hand derivative is negative, okay, negative slope. Whereas if you look at the right-hand side, as you approach 0 from the right piece of the absolute value function has a derivative that's going to give us a positive slope. So a negative slope and a positive slope from both directions. So that's the reason why at a corner, the derivative does not exist. So this is a very nice example for understanding that discrepancy there. Okay. Another condition is when there is a cusp. Okay, a cusp is like this. That kind of a kink. Okay, so some kind of a quick rise. So that's also pointy, as you can see, right? So what happens here is the left-hand derivative is say infinity, and the right-hand derivative, right? Can you see that here? So the left-hand derivative is infinity, and the right-hand derivative is negative infinity. They don't match, right? And they also are not finite. Okay. Then the next condition is the vertical tangent situation. And here too, we have this vertical tangent, meaning your slope of the tangent line is actually a vertical line itself. So we know the slope of a vertical line is undefined. But if you think about the derivative, the left-hand derivative and the right-hand derivative will be the same, meaning they both will be plus or minus infinity, but it's not a finite limit. It should be a measurable number. Infinity is not a number. So you have the left and the right side being the same value in the sense infinity or positive infinity or negative infinity. But then we have the issue that it's not a finite limit. And the fourth condition would be discontinuity. As you can see here, the graph itself is not continuous, right? So we have the discontinuity. And you clearly have totally different limits, right? So the left-hand limit is somewhere down here, the right-hand limit is somewhere down there, up there, and same holds true here because there is a disconnect. And so for all these reasons, you see that discontinuity also indicates that a derivative does not exist. And I can even add another condition, okay? 5. This is something we've seen before, rapid oscillation. So you have the graph oscillating, and then it's so rapid near that P, say that's the P. You really don't know what's happening. And so we have this rapid oscillation that goes up and down P, and there's no way for us to figure out what's happening there. The closer you go, it just keeps going endlessly. Okay. So what this goes to say is, if limit h approaches 0, f of x plus h minus f of x over h, if this exists, it implies that limit h as h approaches 0 from the left must be the same as limit h approaches 0 from the right. In other words, the left-hand derivative must be equal to the right-hand derivative. And of course, it must be finite. Now that concludes our lecture for this section here in Chapter 3. We will continue on with the same chapter in the next video. See you soon.